Hi, and welcome to Introduction to Verilog video. In this video, we'll be covering the basic information of the language, as well as providing a little bit of background. Verilog is referred to as a hardware descriptive language. It's used to model hardware. In our case, we're going to focus on digital hardware. Other examples of hardware descriptive languages are VHDL and System Verilog. Verilog follows the IEEE 1364 standard. It was first developed in the early 1980s, starting with the standard of IEEE 1364 in 1995. After that, some substantial changes were made and IEEE 1364 2001 standard came out, with the latest standard being IEEE 1364 2005. Verilog, it's important to note that Verilog is the predecessor of the hardware descriptive language System Verilog. So while there are a lot of similarities between the syntax, it is important to know that Verilog and System Verilog are two different standards. And in these videos, we'll be mainly focusing purely on the Verilog standard. So Verilog is used for, as we talked about before, was modeling hardware. Hardware descriptive languages can be used for designing ASICs as well as programming FPGAs. They use logic synthesis to take high-level models and break them into smaller gates or transistors, as well as we can use Verilog for simulation and testing our designs. So in this example, I have two examples of modeling, which is a structural model and a data flow model. Both of these are going to produce the same results, as seen here on the right side, as an AND gate and an OR gate. So here in this data flow model, I have three inputs, A, B, and C. I'm ANDing the A and B, and I'm ORing their result with C, and driving it into an output Z. So as you can see here, I have an A and B. I'm ANDing the result, and with that, I'm ORing it with the input C, and then driving it to an output Z. The same is done here with the structural modeling. I have two gates, an AND and an OR. I have an output that's an internal wire that's ANDing A and B, and is being driven to some OR gate with our input C, and then driving our output Z. So basically what Verilog is doing is we're going to write different types of modeling to basically synthesize different types of hardware. Now, while this is a simple example, if we're trying to synthesize, say, an ALU or even a CPU, it's important to note that we want to use different types of modeling at higher levels to help simplify this process. The basic building blocks of Verilog. So Verilog is built around the keyword we call as a module. Inside a module, we have ports, which is an input, output, or a bidirectional port called an in-out. In this videos, we'll be focusing purely on the input and output. Inside a module, we can have variables, which can be a data type of reg or wire, as well as other different types of data types. And inside those modules, we have our procedural blocks, an always block and an initial block. It's important to note, though, the initial blocks are not synthesizable, so they're mainly used for simulation for writing our test benches, whereas always blocks are synthesizable and are mostly used, as you'll see, in our behavioral modeling. Inside our module, we can also have components, calling other modules, which are used for hierarchical design. We can also have assignment statements, which are used for data flow modeling, as well as other functions and tasks. We always end a module with the keyword end module. So different types of modeling. We talked a little bit about this, but there's three main types of modeling. We have structural, or also known as gate level or transistor modeling. This modeling, we use gate level primitives and wire them together to create our digital logic. The next type of modeling, which is a little higher, is data flow modeling. From this one, we can write as basically Boolean algebra and use assignment statements to then model our digital hardware. And finally, we have behavioral modeling. This is the highest level of modeling, and what we can do is we can use if-else as well as switch case statements to model our digital hardware and logic. As you can see, each one will have advantages and disadvantages, which we'll talk about in later videos. Here's an example of a Verilog program. As we start, we have our keyword module. From here, this module's name is test. We have our ports list, input, output, and in first input, we have an input, which is a bit size of 1 that is labeled A. We have another input, which is a bit size 1, is labeled B. We have an output, which is a data type of reg, which is a bit size 1, and it's labeled C. Now, if you don't see a reg usually you can assume that this defaults to wire. So we have an input, which is a bit size 1 wire, A. And this will become important later when we talk a little bit about data types. From here we have our always block, which is our procedural block, an at, and then in here we have these parentheses with an asterisk. This is usually mean that our procedural block is a combinatorial logic, and we'll talk a little bit more about this later too in other videos as well. Now it's important to note when we use a procedural block, if we have multiple lines inside our procedural block, we need to use a begin and end statement to basically indicate the beginning of the procedural block and the end of the procedural block. From here I'm driving my output C with the logic of my input A, and bitwise ANDing it with my input B using a non-blocking assignment statement. And from here, when we're done, we end the module by calling the keyword tag end module. So that's it for the video. If you have any questions or concerns, or you notice anything that was incorrect, please email us at csusiee@gmail.com. Please look out for other videos, and thank you for watching.